Okay, welcome to the replacement lecture for, what day was that, Wednesday the 21st from snow. I have taken the liberty of trying to shorten some things, so I would recommend looking at the PowerPoint for, just some of the extra smaller details. And I've also taken the time to go ahead and write out all the finds and givens just so we don't spend video time doing that. So if you're trying to write along with these, you may want to pause it periodically, at the beginning of a problem, and then write everything down, and then come back and start playing it again. Okay, and so I'm going to try and do it here, and I'm hopeful that everything gets seen okay. I'm going to try and kind of put things over as much as, that may have been right outside the, all right, I'm going to leave it there because I think that's where the video is. In fact, let me go check. Okay, that's where it needs to stay. Okay, so for this class, we are going to look at first a review problem. So this is, again, looking at just finding change in entropy, which is nothing new, just delta S. And so what we have here to begin with is gas in a piston cylinder assembly, isothermal process. We were given the temperature, and we know the change in entropy. And so the question is, if we can assume an ideal gas model, and we don't have kinetic and potential energy effects as usual, evaluate the work in kilojoules. So we're trying to find work. We're given these things. We know piston cylinder simply means it's a closed system. Isothermal means the temperatures are the same. We know the change in S. We know it's an ideal gas. And we know that kinetic and potential energy are negligible. So looking at this and thinking about this, we don't really have a lot of information. I mean, we have a temperature, and that's about it. So, so not really enough information for the table. So partly because it's a gas, and we don't know which gas it is. So if we knew the gas, temperature would be enough, but we don't have that. Okay, so let's take a look at what equation we're going to use. As always, I vote for starting with our trusted closed system energy balance equation. And here, no, we'll just leave it like that. And then we know that KE and PE are going to be negligible. And then we're going to solve this for, we're looking for work out. So we'll go ahead and solve this for work out. And so putting work on the other side, so I get Q minus QN minus delta U. Okay, well, we don't have enough for the table, so what are we going to do? So now we need to think about, is there anything we know about heat and anything that we know about change in internal energy? So let's start with change in internal energy. That's one that we remember from before. So we know that the change in internal energy for an ideal gas is going to be M C sub V delta T. I don't have mass, and I don't have specific heat, but I do know that the change in temperature is 0 because it's isothermal. So 0. So that makes that easy. And then we also have, now we need to figure out an equation that relates heat to anything else on the list. And the only other thing on the list is change in entropy. So we do have this equation. We know that the change in entropy is equal to the change in heat divided by T. Or if we solve that for Q, we're basically going to get delta S times T. Well, we know delta S and we know T, so we're in good shape. So here we're going to have negative 0.3 kilojoule per Kelvin times the temperature, 400 Kelvin. So we get the change in heat is negative 120 kilojoules. Okay, so that, move up just a little bit. So far so good. So change in internal energy is 0. We use this to find something about heat, and so we know that that's negative 120 kilojoules. So that means we know that finally, plugging everything back in, work out is negative 120 kilojoules. Okay, so that one's simple enough. So again, just that was a case where we didn't have enough for the tables, but we have some other equations that we can use. Okay, so let's move on. So here, I just want to go over, these are some equations that I wanted to present So importantly, and as we go through these, like I said, I've already handwritten these out. These are also in the PowerPoint. Importantly about this first section, this is for liquids and solids, incompressible only. So we're going to have a different set of equations for incompressible compared to gases. So here we know this would be for a closed system and assuming that C is constant, which means we can't have too much variation, say, in temperature. So that here we know that the change in entropy is equal to C times the log of the ratio of the temperatures. All right, so that's pretty convenient. We also know for an ideal gas in a closed system, we're going to have similar but not quite the same equations. Again, change in entropy, C sub V, ln of the ratio of the temperatures, but then we also are going to add this other component, ideal gas constant times ln of the ratio of the volumes. Or if we have pressure instead, we have this equation. Or we can replace just this piece of it with this. So let me show you where that is, because that's a little bit different. And importantly, S0 is not entropy. Right? It's not. This is not equal to this. So this is not exactly entropy. So if we look in table A22, you see it, A22. So here we have S sub 0, or S0, because it's not a sub. So we can use those values in that equation instead. So again, in the table, but not exactly entropy. Okay, we also then have a set of equations. I hope you can see this okay. So I'm going to scoot it up a little bit. We have a set of equations now that are based on temperature. And I'm not going to rederive all of these, but we start with our energy balance equation. We use what we know about entropy. We use what we know about expansive work. And we use our definition of entropy, which is related to internal energy plus P times V, the integral of P times V. So here we have one equation based on internal energy and expansive work, and here's another based on enthalpy and another variation of that. We can also write it in terms of specific energy, specific internal energy, specific enthalpy, and specific entropy. So this is just a set of another set of equations that we can use. Typically, out of all of these, the ones that we're going to use the most are these ideal gas equations. These are the ones that I feel like we use more than the others. Okay, all right, so there's that. I feel like I'm talking fast. I'm trying to slow down. Okay, so now we need to look at a couple of things. We need to look at energy production for closed systems and energy production for open systems. So this is kind of the newer material. The problem we just did was kind of a little bit of a catch-up from the last time, and so now we'll look at this problem. This is sort of the start of the newer material. So energy production. I believe we've introduced this before, but sigma is the variable we use for entropy production. And so you can see that it's got this component that we've looked at before. So this is the entropy. What am I writing down? Oh, this is the entropy that's transferred in with heat transfer, and then this is the change of the entropy of the material itself. So that's the energy production for the system. So remember, because this is for a cycle, if it's internally reversible, that means it can be put back to perfection, which means it is perfect, it's not real, then the entropy, that should be a sigma. These should all be sigmas. In fact, I can fix that right now. So if it's internally reversible, then we know that the energy production is 0. If it's internally irreversible, then we know that the energy production is greater than 0. Keep saying entropy production is greater than 0. And then, of course, if entropy production for the whole cycle is less than 0, we know that that's impossible. We can't do that. So all of these are sigmas. Okay, so we have this equation to use then. So let's do an example. So here we have, this is a problem we did before, very similar. So we have a metal bar that's initially very, very hot, 1900 degrees Rankine, and we quench it in a well-insulated tank containing 20 pounds of water initially at 530 degrees Rankine. So equilibrium temperature is 535. We know the specific heat of water, and we know the specific heat of the metal. So find the amount of entropy produced during the process. So we're trying to find sigma. So we know the mass of the metal, and we know the mass of the water, the temperature of the metal, the temperature of the water, and the specific heats for both. Okay, so all my pieces. Okay. Oh, I did miss some. Oh, never mind. I'm good. Okay. All right. So, so what do we know? So let's go ahead and start with an equation. We're trying to find entropy production. So we'll start with that. And I'm going to go ahead and write delta S, S2 minus S1, not specific. I've taken out the mass, and then minus the change in the temperature, change in the heat, what am I trying to say? Change in the heat transfer divided by the temperature of the surrounding, of the boundary. So in this case, because we know that this is a well-insulated tank, we're going to assume then that there is no heat transfer. So we're going to ignore that. So now we have the entropy production is just the change in entropy for the system. So we need to remember then that this is going to be change in entropy for the metal plus change in entropy for the water. We have both components. Okay. Metal, water, both incompressible, so that we know that we can use the following equation. So it looks like we have everything. We have the mass, the specific heat, and the temperatures for both. So when we plug all of that in, we're going to get, first for the metal, the mass times the specific heat times ln of the change in temperature. So T2 is 535. And originally that's sitting at 1800. Both of those are degrees Rankine. Obviously that will cancel. And then we're going to add to that, I'm going to come down here, 20 pounds of water times its specific heat times ln of that temperature difference. Again, 535 is the ending temperature divided by, where did we start? 530. Okay, so adding all of that up, we get 0.0864 BTU per degree R. You see everything? Oh, move that up. There we go. Okay, so again, in this case, we're starting with our equation for entropy production. We know that we have a well-insulated tank, which means that there is no heat transfer across the boundary. So even though we don't know the temperature of the boundary, that's okay, it's well insulated. And so here we have drawn our closed system as being the tank, not just the metal or not just the water, but the whole system. So that means then we just have only the change in entropy. We have to add the component from the metal and the component from the water. We use our incompressible equation, drop everything in, get an answer. Okay, is there anything else? I think that's everything I want to say about that. Okay, and so lastly, before I finish up this video, I'm just concerned that my video camera will only tape a half an hour at a time, so I'm afraid that I may not, I'm going to go ahead and tape these kind of in sections just to make sure that I don't get cut off in the middle and have to start over. Okay, so we've talked about entropy production for closed systems. Now we need to look at open systems. And again, you can look at the PowerPoint for more information. Let me move this down just a little so I can look at it. Okay, so here is our the components. So we have components from heat transfer, from mass flow, because remember this is an open system, so we have the entropy can come in through heat transfer or through what's flowing into the open system, minus what's flowing out, plus whatever is produced. So we have a heat transfer, a mass flow, and a process or production component. So this is the change in entropy, kind of on a time basis. So for steady state, what do we know? for steady state, things are not changing. So that means this is 0. So this then becomes our equation for open systems at steady state. And we can clean it up a little bit just by noting that steady state, m sub I and m sub E, the inlet and exit mass flow rates are the same. So pulling that together, assuming there's only one of each, simplifies it yet further. So now we can solve for this, throw everything else on the other side. And again, remember that we could change this into a plus and reverse the order here. That won't really change. So we're going to come back to that in just a sec, but sort of as a summary then, for balance equations, for a closed system we have energy balance and entropy balance. For open systems we have energy rate balance, mass rate balance, and entropy rate balance. Okay, so I think I'm going to stop there and stop the tape and then start up again when we do, I have 2 examples to do for entropy production for open systems.